Hi, welcome to the backup lecture of CPE214 Signals and Systems. I am Prom-on. This will be the fourth lecture on linear time-invariant systems. Let's begin. Linear time-invariant systems, or an LTI system, is a system that basically possesses two basic properties: linearity and time invariant. Many real-world processes have these properties, and they can be modeled as LTI systems. And since it can be relatively easy to analyze, so we will study them as the main technique in this course. Let's first revise the basic concepts a little bit. A system is linear if it has superposition properties. So if you combine the small input that produce individual outputs together, then you can expect to have the combination of the output of these small systems. This goes for both CT and DT systems. For the time-invariant system, if you give the system with xt and have the output yt, and then you give for the TI system the shifted version of the input to the systems, then you can expect to have the shifted version of the output of the system. Now, since we know that linearity plays a very important role here because the system has a linear property, then we can utilize this type of properties and decompose the signals that we have, a complex signals that we have, into a set of a small sequence of signal. So the idea is to think of, starting from the discrete time, to think of a discrete time signal as a sequence of individual impulse. So from these very complex signals, you can think of them as an individual impulse, like if you multiply the impulse into each terms. So this stem here can be mathematically described as delta n plus 2, meaning that value 1 at minus 2 time x minus 2, the value of x minus 2. And this is delta n plus 1 having the value only at minus 1 and multiplying by the value x minus 1. And this stem is delta n times x0. So the original signal is actually the combination of small impulses, small samples. And we can write it mathematically like this, like the above. That is xn equal x minus 3 delta n plus 3 x minus 2 plus x minus 2 delta n plus 2 x minus 1 delta n plus 1. So when we look at this pattern, we can write them mathematically as xn equal from k equal the summation of from k equal minus infinite to infinite of the value xk multiplied by the impulse delta n minus k. So that this xn is actually the combination of the shifted version of impulse scaled by the values of x. We call this as sifting properties. It's like when you sift through each stems here, each bar here, to get individual values of the stem. So by decomposing the signals into small impulse, we can then process them individually to get the response of the system. So first, we decompose the discrete time signal xn into small unit impulse like this. Then, second step, we give these small signals into the systems. And then for each of these, we get the response out of that. The response will be the impulse response multiplied by the scaling of these signals. In the last step, we can sum the individual output together to get the final output. Because we know that from the linear properties, we can fetch the small version of the signals that are combined to be the big signals and fetch them individually into the systems, then combine them later, we would expect to have the same thing like if you fetch the whole big signals pass through the system. And because we know that the system is linear, then it means that we can add the signals together to get the final output. So let's denote the response of the system to individual impulse as HKN. This denotes the response of the linear system to the shifted unit impulse delta n minus k. So you have this term as response of individual stem. Then by combining them together, you get the output. And because the system is time invariant, then the response to the time-shifted unit impulse are the time-shifted version of each other. That means HKN here is actually Hn minus k, and we will have Hn, which means k equals 0 is the output to LTI system, to delta n when the input is impulse. We call this Hn as impulse response, or for DT, unit sample response. So if we give the system with delta n and we get the output Hn, if we shift the input by -2, we should have something like this, that it is Hn minus 2. And if we shift the impulse by -1 and multiply it by -1 as well, we should have the output like this, that it is minus Hn minus 1, the shifted version of the impulse response by -1 and then multiply it by negative -1. So the output of LTI system can be summarized in this equation, that is Yn equal summation of k from -infinite to infinite of xk, the scaling values, and Hn minus k, the shifted version of the impulse response. We call this equation a superposition sum or a convolution sum, which indicate how we can calculate the output of the system given the input x and the system h. This operation on the right hand side here can be written in a shorter terms and easier to express term. We usually in this course use star sign to denote convolution. Please note that this is different from programming that you use star sign to denote multiplication. But in this case, star denote convolution process. And we will talk more about this convolution process in the next lecture. So I suppose that you all have done this in your in-class exercise. If not, I can give you some clues so that you can work out later. You already have the decomposition part of xn into 3 different impulses. The first one, the second one, and the third one. And you know that if the input is impulse delta n, you have output equals Hn here. So to compute Yn, you need to fetch 3 small signals into the system and get 3 different versions of H and then add them together. Then you get the output Yn. If you want to have a more specific example, or if you have a specific questions about this example, please contact me later. This is the end of the 4th lecture, linear time invariant systems. Next time we will learn about convolution, which is a shortcut on how to calculate the output of the LTI system. So see you then. Bye.